Traffic jams. They're one of the worst parts of automobile travel. They can be caused by accidents, construction, and poor weather, but sometimes they're just the result of poor road design. Traffic engineers work to minimize traffic jams with a number of strategies, including setting appropriate speed limits. This video presents a calculus problem to find the optimal speed limit for a certain road. For this problem, let's assume that the flow rate, F, cars per hour, on a congested highway is found by traffic engineers to be V over 22 plus 0.02 V squared, where V is the speed of traffic in miles per hour. So here, the flow rate of traffic, F, is a function of V, a function of the speed of traffic. So what we will do in this problem is we will use calculus to find the value of V, the speed that will maximize the flow rate of traffic on the road. Here, we are being asked to maximize the flow rate of traffic on the road. We are being asked to find an optimal value for V, an optimal speed limit. Therefore, to solve this problem, to maximize the flow rate of traffic F, we will follow the guidelines to solve a calculus optimization problem. In this problem specifically, that means we will first differentiate F with respect to V. We'll then take that derivative and set it equal to 0, and then solve for V. And that value for V we find at the end will be an optimal speed that will maximize the flow rate of traffic on the road. Okay, so let's work our way through those three steps. The first step is to differentiate F with respect to V, so we will find the derivative of F, which is a quotient, by using the quotient rule. Let's recall that the quotient rule states that the derivative of any function F over G is equal to the denominator unchanged times the derivative of the numerator minus the numerator unchanged times the derivative of the denominator, all over the original denominator squared. In this case, that means the derivative of F is the denominator unchanged times the derivative of V, which is just 1, minus the numerator unchanged V times the derivative of the denominator. The derivative of the denominator here is pretty straightforward. There's two terms. The first term is a constant whose derivative is 0, and the derivative of 0.02 V squared using the power rule is 2 times 0.02, which is 0.04. And then let's drop the power on V down to the power of 1. The denominator of the derivative is the original denominator squared. So here we do have a derivative of F, but let's simplify it a little bit. We can multiply the quantity by 1. We can multiply V and 0.04 V together. Multiplying the quantity by 1 doesn't change anything, so the first two terms are the same. The product of V and 0.04 V is 0.04 V squared. This was a negative times a positive, we could think of it as, so this term is negative. The last thing to do to simplify this derivative is combine like terms. The last two terms are both V squared terms. So 0.02 V squared positive minus 0.04 V squared is negative 0.02 V squared. I wrote that first, and I wrote the positive 22 term second in the numerator. And this is a simplified version of the derivative of F with respect to V. Now that we have the derivative of F, we can move on to step 2, which is where we take that derivative and set it equal to 0. In this case, F was a fraction, and the only way a fraction can be 0 is if the numerator is equal to 0. So setting this derivative equal to 0 is as simple as taking the numerator, negative 0.02 V squared plus 22, and setting that equal to 0. This equation now represents when the derivative is equal to 0. Let's think about what's really happening here. Our function F, which is graphed here, represented the flow rate of traffic. And when you look at the graph, you can see that the flow rate of traffic was increasing. It was kind of getting flowing better and better. More cars were moving. The traffic was flowing better as the speed of the cars increased. But then there was a certain point at which, when cars started to go faster, the flow rate slowed down. We are in this problem. We're trying to find the optimal flow rate. We want to know when the flow rate of traffic is the best. When we found the derivative, we found a formula that tells you the rate of change of the flow rate at every value for v. And when is the flow rate the highest? Well, that happens when the rate of change of the flow rate is 0. Look, the flow rate was increasing. Its rate of change was positive for a while, but then it got to a point where the flow rate started to get worse. The flow rate went down. The optimal flow rate is when the rate of change is 0, which is the same as saying when the derivative is equal to 0. And that's why we set the derivative equal to 0 just now. And what we're going to find after we solve this equation in step 3 is we're going to find the value for v, this value for v, which optimizes the flow rate of traffic, which basically is when the rate of change of the flow rate is 0. We're going to do that in step 3. Step 3 is the final step in this problem, and it is where we take the equation we wrote in step 2 and solve for v. We are done with the calculus part of this problem. All we have to do is solve this fairly simple quadratic equation. We don't need the quadratic formula. The simplest way to solve this equation is to isolate v squared and take the square root of both sides. Let's begin by subtracting 22 from both sides of the equation and then dividing both sides of the equation by negative 0.02. That means that v squared is equal to negative 22 divided by negative 0.02, which is positive 1100. We can then find the value of v by taking the square root of both sides of the equation. In general, when you introduce a square root into an equation, we'll include a plus or minus in front of the number. But here we are finding the speed that will maximize the flow rate on the road. V represents a speed, and a negative speed does not make any sense. So we will ignore the negative, and the square root of v squared is the square root of 1100. So v is equal to the square root of 1100. Because v equals the square root of 1100, this means that the square root of 1100 miles per hour is the optimal speed limit to maximize the flow of traffic. If every car on this road drove exactly the square root of 1100 miles per hour, traffic would flow the best. Perhaps traffic engineers should set the speed limit for this road to be the square root of 1100 miles per hour. Now, I have never seen a speed limit sign that included an irrational number, and it would probably confuse most people, so this is likely not a good idea. The square root of 1100 is approximately 33.166. So I think it could be agreed that a good speed limit for this road would be 35 miles per hour.